Hello everyone. In this video we will do some examples for improper integrals over infinite intervals. So here I have integral from 1 to infinity. So the first step is that, okay, replace that infinity by a variable t and then integrate this one. This is easy integral. This is a ln of absolute value of x, but since everything is bigger than 1, I can just write ln x and then go from 1 to t. This will give me ln t minus ln of 1, but ln 1 is 0, so the result is ln t. It's a function of t, but then we have to bring in that limit, so t now goes to plus infinity. In other words, we are trying to find limit of ln t as t goes to plus infinity. Remember the graph of ln t. So it is something like this. And as t goes to plus infinity, this goes to plus infinity as well. So this means that this limit here is plus infinity. And what does it mean? It means that the integral of 1 to infinity of 1 over x dx is actually divergent series. Well, this integral is one of the a series of integrals which are very important, and they are called sometimes p integrals. So integral from a to infinity of 1 over x to the power p. For example, if p the power is bigger than 1, then, well, a to t of 1 over x to the power p dx, we can write it as x to the power p dx, and then this will, minus p, then this will give me 1 minus p x to the power minus p plus 1, go from a to t, and then when you go 1 over 1 minus p, so t to the power 1 minus p, and minus 1 over 1 minus p a to the power 1 minus p. So if we find the limit of this guy as t goes to plus infinity, you see that we are basically trying to find the limit of this guy. Okay, p is bigger than 1, so I can write this guy as this, t. And in the denominator, that guy is going to be a positive power, so t goes to plus infinity. So this will be 1 over t to the power positive number. I assume that p is bigger than 1. Then 1 over plus infinity, this will give me 0, 1 minus 1 over 1 minus p, a to the power of 1 minus p. And you see that this is convergent. So if p is bigger than that, then the integral is convergent. But as you saw for p equal to 1, while we have a to t of 1 over x dx, this will be ln of t minus ln of a. And then when find the limit, this will be infinity. And I won't repeat this more here, but you can show that for p bigger than less than 1 with the same arguments that we showed up there. But what will happen here is that if p is less than 1, then t to the power p minus 1, we have to keep it in numerator to have positive power. And then when you have t infinity to power any positive number, big numbers, you put it to the power any positive number, this will grow big and big. So that will be divergent as well. So for example, so let me just write this. A to plus infinity 1 over x to the power p dx is going to be divergent. And while examples of this, for example, integral of 1 over root x dx as from e to plus infinity is going to be divergent. So but just by looking at the power, you can say when it is convergent, when it is divergent. When p is bigger than, strictly bigger than 1, it is convergent. Otherwise, it is divergent. Okay, so that's a very important class. Well, actually, this example is also related there. So it says that draw this, the region under 1 over x. 1 over x has a graph like this, yes. So it is like that. So the region from 2, so let me write 2 to infinity. This region, well, goes up to down there, yes. So if you rotate this along the x-axis, oh, the question, I forgot to put that along x-axis in the question. So this is rotating the region under the x along x-axis or about x-axis. Then you know that the volume in that case is going to be given a pi integral of f of x squared dx. But we are going to from 2 to plus infinity. Yes. So we have to check to see if this is convergent or not. So basically we are trying to find 1 over x squared dx. But this is one of these p integrals. P is 2, which is bigger than 1, and it is convergent. So we know that we have to find just one number. What is that number? That number is going to be the volume. So here we go from 2 to t 1 over x squared dx. Antiderivative of 1 over x squared is negative 1 over x. Go from 2 to t, and that is negative 1 over t plus 1 over 2. Now you find the limit of that as t goes to plus infinity. This is the limit of negative 1 over t plus 1 over 2 as t goes to plus infinity. As t goes to plus infinity, 1 over t will go to 0. So this will be negative 0 plus half. So the volume of this object which goes up to infinity is 1 over 2. Well, it's interesting to note that the integral from 2 to plus infinity of the function 1 over x itself is the area under the graph of 1 over x. And we show that this is divergent. This is very interesting, that the guy itself, the region itself, has divergence. So it has divergent area. But when you rotate it, you get this thing. It has convergent volume. It's very interesting this way to see this example. Okay. Let's finish this video with one little bit more general case. So here we are asked to find for which values of p this guy is convergent or divergent. So we are trying to do this one. I'll replace it by t first. What do I do with p? So let's just find antiderivative first, and then do the definite integral and then improper integral. So here you see this is nice. 1 over x dx. 1 over x dx is derivative of ln x. So if I set u to be ln x, du is going to be 1 over x dx. And that way this will be 1 over x to the power p, or when u to the power du. Okay. And well, this way, basically, if we had a limit from e to some t, from e to t, so that would change the limits, yes? So if x is e, then u is going to be ln e, which is 1. If x is t, then that u is going to be ln t. So this will go from e, from 1 to ln t. Okay. So, but this substitution, you see that when you do the substitution, your integral is going to be very similar to the integral of p integrals. Well, the limit is up there. So if you're trying to find limit of ln t 1 over u p du as t goes to plus infinity, you can apply a substitution for the limit. See, if t goes to plus infinity, ln t is going to go to plus infinity as well, yes? That is looking at the graph of ln t. So if I call this one as s, my integral can be written as 1 to s goes to plus infinity of 1 over u p du. And while this is the definition of 1 to infinity of 1 over u p du, this is p integral, yes? And we know that it is convergent, so 1 infinity 1 over u p du is convergent if and only if p is bigger than 1. But what we found here is basically limit of this guy as t goes to infinity. But this means that limit of t goes to plus infinity of e to t1 over x ln x to the power p dx. Yes? And isn't that what we were trying to find? So now this is exactly the integral e to the power infinity 1 over x ln x p dx. So what we showed is that this guy is convergent if and only if p is bigger than 2, strictly bigger than 1, sorry. So with one substitution, you can turn it back to p integrals and then use the result of p integral. Okay. So this way, we had some examples of this very famous family of improper integrals.